Hello, let us try and solve the problem for our assignment. We only have one problem and it is simple. I would say it's not very difficult. The only thing that you have to know or remember is how to derive, how to use calculus, how to solve for a variable, but the concept is pretty straightforward. We're talking about rectilinear dynamics. So basically, we're trying to find the space, the distance, the acceleration, the velocity of body or a system moving in a Cartesian coordinate system. Okay, so before we start, I want to share something with you that will help you somewhat with your problems from now on. So to make things simpler, we should be able to use tool to help us integrate and will help us differentiate. You can use these for other classes too. So it's called Wolfram Alpha. If you go to www.wolframalpha.com, which is right here on the browser, we could go and integrate and differentiate and use math. And for other classes, you can actually use ChatGTP for understanding concepts like material science and other stuff. So, for instance, we know that the derivative of x squared is 2x. So let's see that. If we have x and squared, remember this hat thing is x squared, or x cubed will be like this. So x squared, if we enter that, it will just basically give you the graph. It's not very difficult. This is useful for complicated functions, but x squared is a well-known one. So if you want to differentiate x squared, you simply have to do differentiation of this function with respect to x, right? Very simple. If you want to integrate the function, it's also very simple. The integral of x squared with respect to x. All right, so right here is not evaluated, it's just the function itself that we're integrating. And if you use this, it will simplify things a lot, because a lot of times the issues and the problems are not really solving the question itself, is how to do the math. So this will help you corroborate, clarify, go over the details that you need to know. All right, so back to the problem. So the problem says, right. So yeah, we have a bullet is going downwards. So that is important because that is how we decide to choose our coordinate system. So we can have the coordinate system here or here, and we'll talk about those things. So let's put a coordinate system here. So that coordinate system will be x and y. This is the origin of the coordinate system. You can have it here, but I will tell you what the assumption is if you put it here. All right, so the drag of the fluid. So yeah, given the drag of the fluid, so basically a bullet is going through the fluid and is experimenting a deceleration. So it's basically losing acceleration. And the equation for that is A equals negative 0.4 V3, V to the cubic power. And this is obviously in meters per second squared. All right, so this is the function. And so V is in meters per second. So this is important to know. V is not in feet per second, but it's in meters per second. So we use an international system of units. So they're telling us determine the velocity. So what is V? And also what is the position after 4 seconds? And what is S or X after 4 seconds? Okay, so if you notice, the important thing here is to realize that they're telling us that they're telling us that the initial velocity is 60 meters per second. So the initial velocity here at this point is 60 meters per second. So you have two choices. If you choose, if you were to solve this problem and they're asking you what is the velocity, I don't know, 20 meters above. So like if they're asking you for this velocity here, you'll need a drag of the air, or sometimes you can assume that you don't have any, it's negligible, you don't have any drag, and then the velocity here is the same as the velocity here. So that, I see a lot of you place your velocity here, and that could be correct if you assume that there's no air drag, or if this is not going, if this is going through a material, I don't know, dirt or something, it will be not, obviously it's not the case. But I don't want to complicate things, just a comment that the velocity is 60 at this point when it enters, when it's entering the water or the liquid. How do you know that? You can have a camera, you can have, yeah, probably a high-speed camera, but any other velocity you have to assume or compute, given the drag, or but they don't give us anything else. So really we care about this region. Okay, from the moment it enters the fluid to the point where we're gonna find the distance. All right, yeah, that's what they're giving us. So we know that the acceleration is the change in velocity with respect to time. And that's pretty simple because we have already our acceleration function. So negative 0.4, this is how we solve the problem. 0.4 v3 is equal to the vt. Okay, so again, we know that acceleration is the change of velocity with time, but we also know that velocity is equal to the change of distance with time, or acceleration is equal to the second derivative of your distance with respect to time. So it really depends where your starting point or what you need to solve for. You can start from the distance or you can start from the velocity, but at the end, this is the way you combine these things, okay? Velocity and acceleration and displacement are connected to each other by integrating or differentiating. Okay, good. So the problem, really, the only thing you have to do is solve this equation. And again, you can use Wolfram Alpha, your calculator, you can use calculus. And the way we do this is basically saying, okay, if you remember, we can say that dt is equal to dv over 0.4 v3. All right, so let's do this part first. What is the time? We don't know. We're gonna start at initial condition equals 0. That is the simplest thing we can do. So let's start at time equals 0. And this is going to be t minus 0 or just t. Very simple. Now this part, this is where we're gonna use Wolfram Alpha. Or you just, if you're good at differentiating and integrating, you can just do it yourself. So now for this part, we're gonna say that the integral from where to where? The initial condition is 60, so 60 meters per second, and the final condition is unknown, so the velocity. This is probably the toughest thing to realize. Once you know this, you're good to go. All right, and the second thing is we have to differentiate the function, or integrate in this case, because we're going from acceleration to velocity, right? So integrate, if we're going back, and the function is 0.4 v3. Okay, really, so don't get confused. This is the same thing as saying 60 meters per second v, and the function is 0.4 v3 dv. This is the same thing, okay? Don't get confused. It should be pretty simple to see that. All right, so this is where we can use Wolfram Alpha. So if we go to Wolfram Alpha and we say, okay, we want to integrate a function and the variable is v, and is going to be 1 over negative 0.4, yeah, v to the third power. Let's see if I wrote it down correctly. Yeah. So this is what we're trying to differentiate. Okay, good. So it's 1.25 v squared. So this is 1.25 over v squared from 60 meters per second to the variable v. All right. So again, this is not a number because we're trying to solve for this v when we replace it. So that is basically 1.25 over v squared minus 1.25 over 60 squared. I'm going to leave it like that because then when we replace the time, it will be easier. And you'll see why. Basically, just you don't have to use the calculator until very end. All right, so we have 125 over v squared minus 125 60 squared equals t, which comes from up here, right? This is the other side of the equation. All right, so solving for v, solve for v, we have that 1.25 v negative 2. Remember from math, this is 1 over v squared. You can bring it up with as a negative sign, equals t plus 1.25 over 60 squared. Very well. Then what we can do is bring this 125 over. Let's do it here. So v negative 2 equals t over 1.25 plus 1 over 60 squared. All right. And then what we want is have v by itself. This is good enough. If you give me this, you're good. But v is basically the negative square root of 1, or I don't think I want to say that. I want to say that is negative 1/2. So plus 1/60 squared, negative 1/2. All right, cool. So this is basically your function. This is negative 2. When you bring it to the other side, is negative 1/2. This is the other thing you have to remember from math. This is nothing to do with dynamics. This is just math. Then what we need to do is find the velocity after 4 seconds. Remember, this is a function of time, so we can just put any time that we want. And this is basically 4 divided 1.25 plus 1 divided 3600. And this is to the negative 1/2. Okay, so this is, let's see, 4 divided 125, 4 divided by 1.25 is 3.2 plus 1 divided 60 squared, 1 divided 3600, 0.00027, and that to negative 1/2. All right, just gonna keep 3.2. So this is going to be to the, this is the important part here, how to use the parentheses. So 3.2 to the negative 1/2 is 0.55. So this is equal to 0.55 meters per second. Okay, so we got the first part of the answer. Okay, for the second part, what we need to do is find what is the displacement, or what is the distance after 4 seconds. So remember that for this question, we basically have to differentiate twice. is the second derivative of displacement with respect to time is equal to whatever that is what we need to do, but we already have the velocity. So what we can do instead is the differentiation of the velocity function with respect to time is equal to the distance. All right, so basically we have to differentiate this guy again. So we have to do the derivative of, with respect to time, of t over 1.25 plus 1 over 60 squared negative 1/2. Okay, that will be our distance. So once you differentiate, and this is going to be basically ds, right? So this is going to be when you do your integration of ds is from s to 0. That's where we get the variable that we're looking for, and then you're going to replace your time with 4 seconds. So the same thing, you can just put this in Wolfram Alpha or do it yourself. Differentiate this function and replace your time with 4 seconds and see what S gives you. The answer is around 4.4 meters. Okay.